scientists have confirmed a major breakthrough has been made that could pave the way for abundant clean energy in the future after more than half a century of research into nuclear fusion. Researchers at the US National Ignition Facility in California said fusion experiments had released more energy than was pumped in by the lab's enormous high-powered lasers, a landmark achievement known as ignition or energy gain. So what is nuclear fusion exactly? Fusion occurs when two light atoms bond together or fuse to make a heavier one. The total mass of the new atom is less than that of the two that formed it. The missing mass is given off as energy. Nuclear fusion is what happens in the Sun and other stars and involves joining two atomic nuclei to make one larger one. Both reactions release large amounts of energy, but with nuclear fusion there is very high energy yield and very low nuclear waste production. The National Ignition Facility is a vast complex at the Lawrence Livermore National Laboratory, California. It was built to perform experiments that recreate briefly and in miniature the processes unleashed inside nuclear bombs, enabling the US to maintain its nuclear warheads without the need for nuclear tests. The technology is far from ready to turn into viable power plants and is not able to solve the climate crisis, but scientists hailed the breakthrough as evidence that the power of the stars can be harnessed on Earth. But the experiments are also stepping stones towards clean fusion power. To achieve the reactions, researchers fire up to 192 giant lasers into a centimeter-long gold cylinder called a holrum. The intense energy heats the container to more than 3 million degrees Celsius, hotter than the surface of the sun, and bathes a peppercorn-sized fuel pellet inside in X-rays. The X-rays strip the surface of the pellet and trigger a rocket-like implosion, driving temperatures and pressures to extremes only seen inside stars, giant planets, and nuclear detonations. The implosion reaches speeds of 400 km per second and causes the deuterium and tritium to fuse. Each fusing pair of hydrogen nuclei produces a lighter helium nucleus and a burst of energy according to Einstein's equation E is equal to mc square. Deuterium is easily extracted from seawater, while tritium can be made from lithium, which is found in the Earth's crust. In the latest experiment, researchers pumped in 2.05 megajoules of laser energy and got about 3.15 megajoules out, a roughly 50% gain, and a sign that fusion reactions in the pellet were driving further fusion reactions. The energy production took less time than it takes light to travel 1 inch. Immense hurdles remain, however, in the quest for fusion power plants. While the pellet released more energy than the lasers put in, the calculation does not include the 300 or so megajoules needed to power up the lasers in the first place. The National Ignition Facility lasers fire about once a day, but a power plant would need to heat targets 10 times per second. Then there is the cost of the targets. The ones used in the US experiment cost tens of thousands of dollars. But for a viable power plant, they would need to cost pence. Another issue is how to get the energy out as heat. In the Sun, massive gravitational forces create the right conditions for nuclear fusion in the star's core. But on Earth, they are much harder to achieve. Fusion fuel, which are the different isotopes of hydrogen, must be heated to extreme temperatures of the order of 50 million degrees Celsius and must be kept stable under intense pressure and dense enough and confined for long enough to allow the nuclei to fuse. In some senses, everything changes. In another, nothing changes. This result proves what most physicists always believed: fusion in the laboratory is possible. However, the obstacles to be overcome to make anything like a commercial reactor are huge and must not be underestimated. Challenges remain of how you can get the energy out of the system, how you can sustain the energy for long enough to be useful, how you scale up that energy, and whether the energy can be cheap enough to compete with other sources. It is highly unlikely that fusion will impact on a timescale sufficiently short to impact our current climate change crisis, so there must be no letup on our efforts in that regard.